In this lesson, we're looking with integration using trigonometric identities. Remember, we've got our three identities here. We've got sine squared is equivalent to 1 half of 1 take cos 2x. We've got cos 2x is equal to 1 half of 1 plus cos 2x. And then we have 1 plus tan squared x is equal to sec squared x. Okay, so in this first example, we've got the integral of 2 cos squared x dot dx. So if we pull that 2 in front, we've got 2 multiplied by the integral of cos squared x dot dx, which means we've got 2 multiplied by the integral of, so cos squared is 1 half 1 plus cos 2x dot dx. 2 multiplied by half is 1, so we're just looking at the integral of 1 plus cos 2x dot dx. So we've got the integral of 1, and we've got the integral of cos 2x, which leaves us with x plus 1 half sine 2x plus c. Okay, so pretty straightforward. If we wanted to apply this double angle, we could say that was equal to x plus 1 half times 2 sine x cos x, or that is x plus sine x cos x plus c. Okay, so you should see that that's nice and straightforward. In this next example, we're looking at the integral of 2 plus 5 sine squared x. Now sine squared x is 1 half of 1 take cos 2x. We have 5 lots of 1 half of 1 take cos 2x dot dx. So if we expand this out and simplify, we've got 2 plus 5 on 2, lots of 1 take cos 2x, and so that means that we've got 2 plus 5 on 2 take 5 on 2 cos 2x dot dx. And 2 is the same as 4 on 2, so now we've got the integral of 9 on 2, subtract 5 on 2 cos 2x dot dx. So working with that to manipulate first makes this a much easier problem. Integral of 9 on 2 is 9 on 2x. Integral of 5 on 2 cos 2x will be 5 on 4, because we have to divide by 2, and then sine 2x plus c. And we can leave it like that, or we can again let that sine 2x be 2 sine x cos x, and we have 9 on 2x take 5 on 2 sine x cos x plus c, or 1 half of 9x take 5 sine x cos x plus c. Okay, so the application can be a little bit more complex, but as long as you go through the process of simplifying first before you integrate, then the outcome is pretty straightforward. Alright, in this next example, we're looking at the integral of 4 multiplied by sine squared 5x dot dx. Okay, so this one's, we have to think a little bit more. Now we're not going to use x in our definition of the rule. We're going to say that sine squared a is equal to, now let's go back up to our rule, it's 1 half 1 take cos 2a in this case. 1 half 1 take cos 2a. Now, if we let a equal 5x, then it's pretty easy to see what we're going to do here. We can say that sine squared 5x is equal to 1/2, 1 take cos, then we've got 2 times 5x, which means we're looking at 1/2, 1 take cos 10x. So this little side calculation means that now we can look at 4 times the integral of sine squared 5x dot dx as 4 times the integral of 1/2, 1 take cos 10x. Now 4 times 1/2 is 2, so we've got 2 lots of 1 take cos 10x dot dx. So that means we've got 2 multiplied by x take 1 on 10 sine 10x plus c. So we have 2x take 1/5 sine 10x plus c. Okay, next example, if we take out the common factor of 5, we've got the integral of 5 bracket 1 plus tan squared x dot dx. Now, go back up and we can see that 1 plus tan squared x is sec squared x. So that means we've got 5 times the integral of sec squared x dot dx. And that means we've got 5 tan x plus c. So a very simple scenario there, taking out the common factor to turn it into our 1 plus tan squared x. 1 plus tan squared x is equal to sec squared x. And we know that the integral of sec squared is tan. So our next one is a little bit more complex because there's a little bit more manipulation. So what we want to be able to do is manipulate this -3 into 2 parts. So the integral of 2 tan squared x. Now we need to have a plus 2 here. So if this is plus 2, then for it to stay at that original -3, we need to have a take 5. So just to follow, plus 2 take 5 is the same as -3. We've just manipulated it. And so now we can say we've got 2 lots of tan squared x plus 1, or 1 plus tan squared x take 5. Which means we've got the integral of 2 sec squared x take 5. So we have 2 times the integral of sec squared x with respect to x, take the integral of 5 with respect to x, and we've got 2 tan x take 5x plus c. Okay, so something that looked more complex is simple if you manipulate it in the right way. Okay, so now we'll look at our last example. Now I think the easiest way to approach this one is to expand it out. We're looking at the integral of 1 plus cos x all squared. So that means we've got 1 squared plus 2 times 1 times cos x, so 2 cos x, plus cos squared x. So it means we end up with the integral of 1 plus 2 cos x plus cos squared x dx. Now we know that cos squared x is equal to, let's go back up to the top, cos squared x is equal to 1/2 of 1 plus cos 2x. So we've got 1 plus 2 cos x plus 1/2 of 1 plus cos 2x dot dx. And if we break this up, we've got 1 plus 2 cos x plus 1/2 plus 1/2 cos 2x, and that means we have now 3 on 2 plus 2 cos x plus 1/2 cos 2x dot dx. So now we can integrate each separately. So we have 3 on 2x. We have 2 sine x, and we have 1 on 4 sine 2x, and don't forget Charlie, so plus c. Now we could leave it like that, or we could say this is 3 on 2x, our 2 sine x, and 1/4 sine 2x is 2 sine x cos x. So we have 3 on 2x, we have 4 on 2 sine x, and we have 1 on 2 sine x cos x, which leaves us with 1/2 3x plus 4 sine x plus sine x cos x plus c. So that will be our final answer. So again, it's that manipulation first before integrating that makes the problem more accessible. Okay, so that concludes the lesson and the examples with integration using trig identities. Hopefully that makes sense. Again, it will take practice and fluency to ensure that you can do this in exam conditions.